In the second lecture, we will be concerned about this question, which sound very qualitative, but we will make it quantitative. How much does a curve is curved? What does it mean? That we have to define, we have to assign to a curve a quantity called curvature. And all of you have some physical notion of curvature, that is how much you have to bend if you move along the curve. And our intuition tells us that a curvature, if at all I can define such a quantity, this should be okay. First one, unchanged under reparameterization. This is a pretty natural demand. Suppose I am moving in a circle and you are also moving on the circle, and you are moving in the speed which is double than me, but I should be bending as much from a point as you should be, however the speed be. And reparameterization is actually saying the how much actually how much speed you are moving in. And all of you should agree that it is not very bad to propose this condition also, that a straight line should have 0 curvature, because if I move in a straight line, I do not bend at all. So, straight line should have 0 curvature. And third I explain you pictorially. So, suppose on the plane you are moving on this circle, or I am moving on this circle and you are moving on this circle. And the radius here is r and radius here is r. So, suppose at this point where and somebody is seeing us on this line, when I am moving, let us say in a cycle, in a bike, then obviously he should see me bending more than how much you bend here at the same point when he is seeing that. Or you can imagine it that when in a bicycle race there are different circular tracks, the person who is on the inner circle bends more than the person who is on the outer circle. The same while people are taking a athletic run or something. So, I put that as a condition that larger circle should have smaller curvature, right. Now, suppose I start thinking about a quantity about a curve which satisfy all these three, then perhaps I should be proposing for curvature a quantity k t, which is the rate of change of speed and its absolute value. But the problem is this will depend on parameterization. So, the first condition will be a problem, but I know if I working on a regular curve, then I have a unit speed parameterization. So, let us say gamma is unit speed, then I can propose curvature to be rate of change of speed and its norm, and you can easily verify this satisfies one, 2, 3. For example, let me show for a circle of radius r, center at point x naught y naught. Well, this is an exercise I put that the unit speed parameterization of above is x naught plus r cos s by r and y naught plus r sin s by r. Now, if you calculate gamma s and then gamma double dot s, that will be, you can calculate very easily. I write directly gamma double dot s is equal to minus r s cos r minus 1 by r sin s by r. So, gamma double dot s is equal to the curvature is equal to 1 by r. So, if r is more, curvature is less, and that is what I wanted. So, this quantity K s equal to gamma double dot s and its norm we will refer as absolute curvature, because later on very soon I am going to introduce what is called sign curvature. However, there is a problem. Suppose I have given a curve to you from some interval a b to r, let us say planar curve r2 or r3. Now, finding its unit speed parameterization may be problem in itself, in the sense that how do you find unit speed parameterization? Okay. First, you can consider the arc length, okay. Then you consider s as a function of t, and then you write gamma tilde s is equal to gamma phi s, and in that case phi has to be s inverse. So, I have to have invert this function. Inverting a function in general is not an easy task to do. So, finding an unit speed parameterization for a curve is in itself is a difficult task. So, need a formula. What I mean here, need a formula to calculate curvature from gamma itself, and the formula I write it as a theorem that suppose gamma is a curve from a b to r n, then k t is equal to gamma double dot cross product gamma dot norm divided by gamma dot cube. Okay. I will not prove this. This proof is available in any standard book. So, proof is a part of assignment. It is just you look at the unit speed parameterization of gamma and calculate K s in terms of K t. So, to a curve I got another quantity which is called curvature, which is has some absolute value. I mean, it is a positive number. So, but to determine a curve, I often need to consider other parameters related to a curve. Okay. One is this, you suppose I have a curve like this, so you have a curve out here, gamma t, here is a point t naught, or let us say it has unit speed s, I have a point s naught here. So, this is gamma dot s naught is the, you can also interpret as a tangent vector. That is a tangent vector. If I rotate the tangent vector by angle pi by 2 anti-clockwise, so rotate this fellow anti-clockwise by pi by 2, then I get another vector. Suppose I take unit speed parameterization, then gamma dot s naught has length 1, and therefore, this eta s naught will also have norm 1, because I am just rotating a vector of, rotating a vector does not change its length, and so this fellow is called unit normal. You see, for the same curve, if I am moving from, let us say, point A to B, then I am moving this way, right. So, the direction of the tangent is that what one I have drawn. But suppose I move from B to A, the direction of the curve will change and direction of the tangent will also change, and so does the unit normal, because I am moving anti-clockwise. In that case, this will be the unit normal. So, it depends on how I move from A to B or B to A. So, this unit normal fellow, direction of that depends on how do I move, and that will give rise to a quantity called orientation. We will soon come to it. Okay. Now, see, if suppose t is a tangent vector, that is gamma s, T s. What is the length? 1, right. That would tell you that T dot, which is gamma double dot, this is perpendicular to T. So, that will imply T dot is parallel to eta. Suppose I have two parallel vector eta and T dot, and those both of them has unit length. So, eta will be some multiple. So, eta s at a point will be multiple, some multiple k s T s. Since I have k, which is I define absolute curvature, equal to so this quantity k s, this is called the signed curvature. Of gamma s. Okay. this sine curvature, this is absolute value is curvature, but this fellow has nice geometric interpretation. And do it in the next page. Okay. Let me go to the board again. Suppose this is my curve, here is the point and this is the tangent vector, unit tangent vector T s, and this is eta s. So, what is the geometric interpretation of K s? Okay, what I do? So, take any unit vector, unit vector, let us say A. Okay. Consider the angle between A and tangent vector. Let us call it phi s. A is a fixed. Once you take it, is fixed. Okay. Now, what I do? I rotate this vector A by an angle pi by 2. So, I get a vector B. So, my T s now, since this angle is phi s, will be resoluted as A cos phi s plus B sin phi s, right, simple geometry. Keep the picture in mind. So, your T is A cos phi s plus B sin phi s. Now, you calculate T dot, which is A sin phi s B cos phi s d phi s ds. This will give us from the previous consideration K s into eta s dot A dot product is equal to T dot product A is equal to minus sin phi s d phi ds. Now, angle between eta s and A is how much? Phi s plus pi by 2. So, eta s into A, both are unit vector, is cos phi s plus pi by 2 equal to minus sin phi s. So, if you combine these two equation, what you get is K s equal to d phi s ds. What does it mean? It means if you take any unit vector, sine curvature is the angle or rate of change of angle phi to which you must move A to make it parallel with T s. Now, we will ask all of you to think of a physical interpretation of this mathematical explanation, that K s equal to this quantity. So, what should be a physical interpretation? I am not telling you, you ask yourself. So, think of a physical interpretation of this quantity, that suppose somebody is moving in a curve and you are an observer standing wherever, what is the sine curvature is? I am standing, and so you think of this situation, that somebody is moving in a cycle in some curve, you are standing somewhere and somebody is standing just opposite to you on a straight line. So, and both of you are observing, what will be the sine curvature for you and for your friend? In the last part, maybe I will continue this in the next lecture also, we will be concerned about determination of unit speed planar curves. That means, I have curves in R 2, and what I want to say here, that I want to make a statement here, a unit speed planar curve is essentially, so essentially I have to make it mathematical, determined by its sign curvature. I will not prove this as a theorem, because in the next lecture we will prove some general theorem about special curves in R 3, from which this will follow. But I want to tell you right now that how the sign curvature determines a curve. So, first let us see, suppose I have a function like this, which is smooth function. Smooth function means always a derivative exists. Fix any S naught in alpha beta and define this quantity phi s equal to S naught to S k u du, and consider gamma s integral S naught to S cos phi u du integral S naught to S sin phi u du. So, what will happen? What is gamma dot? What is phi dot s? This is cos phi s sin phi s. So, this is a unit vector making an angle phi s with x axis, right. Now, what we just observed from here, from the previous page, that means here, that the sign curvature of this implies from previous page, sign curvature of gamma is k s, because this is a vector phi s cos phi s sin phi s. If I rotate it by angle phi s and angle phi s, it will be parallel to x axis, and I know precisely that is a sign curvature. So, sign curvature of gamma is k s. So, what it says that if I have given a smooth function on any interval, I can, given a smooth function k on any interval, I can determine a curve whose sign curvature, I can find out a curve, this one, whose sign curvature is k s, and the converse is also true, in the sense that suppose that I have a curve gamma tilde from alpha beta to R 2 which is unit speed with sign curvature k s, let phi s be the angle between x axis and gamma dot. Then from the discussion above, I know gamma dot s, okay, I mean phi s is the angle. So, gamma dot s can be written as cos phi s sin phi s, that will imply now d phi ds equal to k s, that I know from previous discussion, this will give us that phi s is equal to S naught to S k u du phi of S naught. Okay. So, I can find this angle phi s given a unit speed curve and a sine curvature k s. So, essentially a curve in R 2 is determined by its sine curvature. Now, when you move to spatial curve or curve in R 3, we will show this is not true, and in that case also we will observe something about planar curves, that planar curves are actually, I will write it down as a theorem, that it is exactly determined by its sine curvature up to some rigid motion of the plane. Okay, next lecture.